The Brooklyn Bridge has stood strong for over 140 years. Every single day, 120,000 cars cross it safely. But here's what most people don't realize. This entire massive structure hangs on 14,000 miles of steel cables. That's enough cable to stretch halfway around the planet. But how do you create steel threads strong enough to hold up a bridge that weighs 14,680 tons? The answer lies in one of the most incredible manufacturing processes on Earth. Welcome to The Making, where we reveal the amazing processes that build our world. This is the ultimate engineering challenge. A single steel cable thinner than your wrist must support the weight of 50 cars. That's over 100 tons hanging from threads of twisted metal. Every year, the world uses over 10 million tons of steel cables. They lift elevators in skyscrapers reaching toward the clouds. They anchor massive oil rigs in stormy seas. They support wind turbines generating clean energy for millions of homes. But steel cable was born from desperation. In the 1830s, deep in German mines, hemp ropes kept snapping under heavy loads. Miners were dying. Something stronger was needed, and that something would change the world forever. Today, we're following the epic journey of steel cable, from raw earth deep underground to the cables that hold up our civilization. Our story begins half a mile underground, in mines so vast they could swallow entire city blocks. This is where the raw power of steel cables first awakens. Watch as massive drill systems bore holes into solid rock. Then, controlled explosions fracture the earth, releasing chunks of reddish-brown iron ore that have been sleeping underground for millions of years. Enormous machines with hydraulic arms lift boulders weighing 50 tons each. That's like picking up 25 cars at once. These monster trucks, each carrying 400 tons of raw ore, move in endless convoys toward the surface. At the surface, the raw ore gets its first taste of precision. Vibrating screens shake away dirt and sand. Powerful magnets pull out unwanted metals. What emerges is pure iron ore, ready for its transformation into something that will one day hold human lives in its grip. Welcome to the heart of transformation, the electric arc furnace where raw ore becomes liquid steel, hot enough to melt copper in seconds. Those giant carbon electrodes you see? They're taller than telephone poles and carry enough electricity to power a small city. When they strike the metal, they create artificial lightning that reaches 3,200 degrees Fahrenheit, hot enough to turn solid steel into glowing liquid fire. But creating cable-grade steel isn't just about heat. Watch as engineers add precise amounts of manganese to boost strength, chromium to fight rust, and silicon to keep the steel flexible. It's like a recipe for super strength, mixed one element at a time. See that foam floating on top? That's slag, a natural filter that absorbs dirt and impurities like a magnet. When it gets skimmed away, what remains is pure, powerful steel ready for its next incredible transformation. The molten steel can't wait. It flows immediately into water-cooled copper molds. In seconds, liquid metal becomes solid steel blocks, still glowing red-hot from their fiery birth. This is where steel gets its strength. In the rolling mill where massive forces forge ordinary metal into cable-grade super steel. These rollers weigh 20 tons each and spin with enough force to crush a car. Watch as red-hot steel blocks get squeezed and stretched like taffy, growing longer and thinner with every pass. Here's the amazing part. This isn't just changing shape. The intense pressure actually rearranges the steel's internal structure at the molecular level, making it stronger and more uniform. It's like giving steel a complete workout that transforms it from ordinary metal into super material. High-pressure water jets create dramatic steam clouds as the steel cools in perfectly controlled conditions. Cool too fast and it cracks, too slow and it loses strength. This precision cooling locks in the steel's new superpowers. Now comes the incredible shrinking act, transforming thick steel bars into hair-thin wires strong enough to lift cars. Watch as steel gets pulled through a series of diamond-hard dies, each one smaller than the last. It's like squeezing toothpaste through increasingly tiny holes, except this toothpaste weighs tons and could cut through concrete. Laser sensors measure the wire diameter to within fractions of a human hair. Computer systems adjust the pulling force thousands of times per second. Even the slightest mistake could snap the wire or make it too weak for life-or-death applications. What emerges are perfect coils of high-strength steel wire, each strand precisely engineered to carry massive loads while remaining flexible enough to bend and twist without breaking. Every wire must now survive the ultimate test, a trial by fire that will determine if it's worthy to protect human lives. Inside this furnace, temperatures reach 1,300 degrees Fahrenheit. The controlled atmosphere changes the steel's crystal structure at the atomic level, like rearranging the building blocks of strength itself. Then comes the critical moment: rapid cooling that locks in the steel's new molecular structure. Jets of high-pressure air cool the glowing wires in seconds, freezing their strength at the perfect level. Every wire gets tested for strength, flexibility, and durability. Machines pull them until they break, bend them thousands of times, and subject them to forces that would destroy ordinary metal. Only the strongest survivors move forward. Before these wires can face the real world, they need armor, protective coatings that will keep them strong for decades. Watch as each wire gets dipped in molten zinc at 850 degrees Fahrenheit. This creates a sacrificial armor that will corrode away over years, protecting the steel underneath like a bodyguard taking bullets for a VIP. For the harshest environments, wires receive advanced polymer coatings applied under precise temperature and pressure conditions. These synthetic shields repel water, resist chemicals, and extend the cable's life from decades to generations. Advanced sensors scan every inch of coating, looking for microscopic gaps that could let in moisture. Even a pinhole weakness could eventually destroy an entire cable, so perfection is the only acceptable standard. This is where individual wires become a unified force, twisted together in a mechanical ballet that creates cables stronger than the sum of their parts. Dozens of wire spools rotate around a central core in perfect synchronization. It looks like a massive mechanical flower opening and closing, but it's actually creating the helical pattern that gives cables their incredible strength. Every wire must be pulled at exactly the right tension. Too tight and it snaps, too loose and the cable becomes weak. Computer systems monitor and adjust the tension on each individual wire hundreds of times per second. Watch as layers build up like a spiral staircase. The inner core provides stability, middle layers carry the main load, and outer layers resist wear and damage. Each layer has a specific job in the cable's mission to protect human lives. Before any cable leaves the factory, it must prove itself worthy. In tests so extreme they would terrify the cable's future users. Massive hydraulic machines pull cables until they completely snap, testing their absolute breaking point. A cable rated for 100 tons might actually hold 200 tons before failing, providing a massive safety margin. Bending machines flex cables millions of times, simulating decades of real-world use in just hours. Cables that will hold elevator cars must prove they can bend smoothly millions of times without weakening. Salt spray chambers simulate ocean conditions. Vibration tables shake cables with earthquake-force tremors. Temperature chambers freeze and heat cables through extreme weather cycles. Only cables that survive every torture test earn the right to support bridges, elevators, and cranes. Those that fail get melted down and recycled. They're still living to fight another day. The final step is both art and science. Coiling finished cables without damaging their precisely engineered structure. Robotic systems wind cables into perfect spirals, with computer-controlled tension preventing kinks or overlaps. Each coil is like a massive spring, storing incredible potential energy. Heat-shrink film and oil-resistant cloth wrap each coil like armor, protecting the cable during transport. Every coil gets tracked with codes that trace its history back to the original iron ore. Specialized trucks with anti-roll compartments carry these coils to construction sites around the world, where they'll begin their life mission of keeping people safe. These cables don't just hold up bridges, they hold up civilization itself. Every day, over 1 billion people trust their lives to steel cables and elevators. Without these twisted steel threads, skyscrapers would be impossible and modern cities couldn't exist. Construction cranes use steel cables to build the towers that define our skylines. Suspension bridges like the Golden Gate span impossible distances thanks to cables that distribute millions of tons of load. Wind turbines generating clean electricity depend on cables for stability. Oil rigs in the deepest oceans anchor themselves with cables strong enough to hold against hurricane-force waves. When these cables finally retire after decades of faithful service, they get recycled back into new steel, beginning the cycle again and proving that great engineering never truly dies. From deep underground mines to the Brooklyn Bridge cables, still serving after 140 years. This is the power of precision engineering and human ingenuity. Today's cables are even stronger and more durable than those that built yesterday's wonders. They're supporting space elevators in development, anchoring floating cities, and enabling renewable energy projects that will power the future. Every time you step into an elevator, cross a suspension bridge, or benefit from wind energy, you're trusting your life to these twisted steel threads, each one crafted through this incredible journey from earth to sky. The next time you see steel cables, remember, you're looking at one of humanity's greatest engineering achievements, twisted metal that holds our world together, one strand at a time. What amazed you most about this incredible steel cable journey? Share your thoughts in the comments below. And if you want to see more amazing processes that build our world, hit that subscribe button and notification bell. Because here at The Making, we believe understanding how things are made helps us appreciate the engineering marvels we depend on every single day.